Today, hearing loss or deafness can be compensated with medical devices called a cochlear implant. But for a small group of patients who have a damaged inner ear, the cochlear implant is not suitable. Instead, we need to deliver the sound information to the auditory brainstem, and this can be done with an electrode array called the auditory brainstem implant. A challenge with current clinical ABIs is their relative stiffness, so that the electrode do not selectively stimulate the auditory brainstem. We teamed up with a group of Professor Danley at Mass Eye and Ear in Boston to design a novel technology to manufacture soft auditory brainstem implants.
One of the challenges was that we wanted to use the same materials that are used in the clinic, but these materials are rigid. So we introduced a way to engineer elasticity in these same materials. And so our idea can be explained very easily with this plastic foil. So this is a plastic that cannot be deformed, but as soon as you introduce some cuts, and that was inspired by the Japanese art kirigami, which is the art of cutting paper, we optimize shapes like these Y shapes that we can cut in films, and it allows stretchability. And this same concept was applied on the macro scale, not only on plastic foils, but also on metals, such as platinum, to engineer elastic and soft ABIs. So we first engineered ABIs scaled for mice, so we can test if the devices were functional and could stimulate the auditory pathways, and that was done successfully in animal models. And in a second step, we wanted to make sure that devices could be made for humans. And with our collaborators in Boston, we validated that these new devices, soft ABIs, were compatible with surgical techniques that are already used in the clinic today, as well as imaging such as MRI. And now there's a lot of steps that still need to be done before we can actually test it in humans.